Hey, we're going to talk about net change and accumulation in calculus. And if you want to print the sheet that I'm going to use for guided notes, you can go to bit.ly/net change if you want to follow along with that. And so let's talk about these two topics. And I covered with my students the idea of accumulation a while ago, and just a little reminder that if you are given something's rate of change, that can be given as a derivative, it could be velocity, it could be any number of things, but if you're giving something's rate of change and you need to know the amount of change over a certain interval, then you find that by measuring the area between the rate of change and the x-axis. So before we get into the net change theorem, I'm going to do one quick example of this, and this is stolen from an AP problem from 2002, I believe. I altered it slightly, but it tells you that the rate that people enter an amusement park, and the key phrase here is indeed rate. So this is the rate that people enter the amusement park. Pay attention to units, that is people per hour. And we have this ugly function. It asks how many people, given this rate, how many people enter the park between 12 noon and 5 p.m. And to do that, we're going from a rate, people per hour, and we want only people in the end. That will be the antiderivative from 12 to 17 of the function e of t dt. And if you want to know if your setup is reasonable, there are times where you can actually inject units into the setup. And if you look at e of t is in people per hour. So I'll abbreviate that, people per hour. dt is actually a reference to a change in time, and time in this problem is measured in hours. So what I have in this antiderivative is literally people per hour times hours. And when you multiply those two, you can see the hours will divide out, and you're left with only people, which is what I want. And so the antiderivative of the rate does give you the total amount. As far as getting the answer for this one, we'll use a calculator, and I am going to use Desmos instead of my TI Inspire, which I typically use. So let me go over Desmos here. And you can see I've already stored the function for e of t. And if you want to type a definite integral into Desmos, that is not at all what I wanted to do. Control Z, good, okay. If you want to enter a definite integral into Desmos, you can go through the little keyboard down here and find the definite integral notation with this, and it's not doing it for me right now. I have learned that if you simply type in the letters I, N, and T, as soon as you hit T, pops up the definite integral, and we are measuring the definite integral from 12 to 17, and I am tabbing my way through the different fields of the function e of t, which I previously defined, and as soon as you hit dt, you get your answer of 3494.616. So the answer is 3494.616. And in this problem, I probably should have said this, round to the nearest whole number would be standard when we're talking about the number of people. So we would say that is 3,494 people. Okay, so there's a quick review of accumulation using the rate of change of something to get the total amount of something that changes over the interval. Let's extend that to the net change theorem, and a quick reminder of the evaluation theorem, which this is part of the fundamental theorem of calculus. If you have the antiderivative of a function, so if cap f is the antiderivative of little f, then the definite integral of little f is the antiderivative evaluated at b minus that same antiderivative evaluated at a, and that is something that hopefully you have been doing for quite a while now. But I'm going to take that little expression, the evaluation theorem, part of the fundamental theorem, and I'm going to twist it just a little bit by doing something very mundane, and that is I'm going to add f of a to both sides of this equation. And if I add f of a to both sides of the equation, it no longer exists over here, and we have f of b is equal to f of a plus this integral, which is essentially the formula that I will use for the net change theorem. So it is your evaluation theorem, just with a tiny little alteration where we move one of those evaluated points. In this case, I used f of a and I moved it to the side of the antiderivative. And the main idea behind this is that if you are given something's rate of change, so if we're given something's rate of change, it could be worded like this, where cap f is the antiderivative, but if you have something's rate of change or derivative and you have some initial condition, you can find the amount at a different time by adding the total change from a to b. So let's look at, I'm going to underline this part, the total change from a to b. That's what the definite integral finds. The integral under the rate gives you the total change, and if you know how much you have changed, And you know how much you started with, the initial amount. That's f of a. So if you have what you started with, and you add the change to that, then you get what you finish with at the end of the interval. And so there's the setup that we're going to use for several examples. I'm going to have 5 examples that will hopefully make this a little bit more clear for you. And so let's look at some of these. And the first one is a little bit of an oddball because I could have given this to you, or your teacher, whoever your teacher is, could have given this to you a long time ago, and you probably would have been able to figure it out because, let's see, we have a continuous function. I give you the, okay, so we have the derivative, right? So we have the derivative, we have the rate of change, and I gave you some initial condition. So there's the initial condition, and I want the amount at a later time. So we could use the setup that I just showed you. However, we could also just channel old knowledge, right? I could say, well, f of x, the antiderivative of that would be x squared minus 7x plus a c. And you know what? I have an initial condition. I could solve for c, couldn't I? So f of 3 would be 3 squared minus 7 times 3 plus c. And that's supposed to give me a 4. Well, let's see. What does c need to be so that that's true? 9 minus 21 is negative 12 plus c is 4. We find out c is 16. So now that I have my c, I could reset my function. F of x is x squared minus 7x plus 16. And if I want f of 5, I can simply plug in 5. 5 squared is 25. 7 times 5 is 35 plus 16. That's negative 10 plus 16. I am getting 6 in the end for f of 5. And that is an absolutely 100% fine way of doing this. And you may be thinking, well, if that works, why do I need to know this little setup? If I can just use antiderivatives and solve for c, what's the point of the new setup, the evaluation of the net change theorem? And the reason we need to know it is because you can get a question like this, where you have to have a calculator, and it's the same situation. F is differentiable. I give you f prime. I give you the initial condition. I want the function's value at some later time. I want to know where we are at 2, and I know we're starting at 0, 5. The problem with this one is I have worded this one so that the antiderivative of this function, I'm just going to go ahead and say it's impossible. There are some higher levels of calculus where you might could manage to work through that through something called non-elementary functions. But in AP Calculus, you will not be able to find that antiderivative in order to solve it the same way we did number 1. And so for this one, we have to use that net change setup. So we're given the derivative. We have an initial condition. And I want to know where I am at a later time. And so what I'm going to do is I'm going to start with what I know. I'm starting at f of 0. I need to know how much this function changes from 0 to 2. Well, the amount of change in a function is the integral from 0 to 2 of the derivative, x cubed plus e to the 0.1 x squared. And that will give me f of 2. So I have my initial amount, what I start with. This will tell me, the antiderivative tells you how much f changes. So my initial point plus the change tells me where I finished. And for this one, we're going to have to throw this straight into a calculator, and calculators will have a way to get approximate values for antiderivatives where an explicit antiderivative or a general antiderivative cannot be easily found. So I'm going to go to my calculator. And f of 0 is 5. So I'm going to go back to my calculator. That is not what I wanted to do. I want to go to Desmos. There we go. Let me clear this out. And back to the problem. It's f of 0, which is 5, plus the antiderivative, int, from 0 to 2, of the derivative. And we have to put this in parentheses in Desmos. And my derivative is x cubed plus e to the 0.1 x squared. So x cubed plus e to the 0.1 x cubed. And it's x squared, isn't it? Not x cubed. I did not mean to start my inspire. Go away! Come on, I say go away. There we go. Double check that, and it is indeed x squared. When you're using your calculators, make sure you punch everything in correctly. So I'm plugging this into my Desmos calculator, and I'm getting 11.3019. And that will be your answer, 11.3019. So your initial condition plus the change from x equals 0 to x equals 2 gives you your final resting position, or your final amount at the end of that interval. Let's see, let's look at number 3. There we go. Okay, so here that's presented just a little bit differently. This time, instead of an equation for f prime, I gave you a graph for f prime. But we do have the derivative, so we're given the derivative. We have some initial condition. What I need to know is how much the function changes from 0 to 1. And so it's going to be my amount at 1 is my initial amount, f of 0, plus, and then to find the change in the function, if I want to know how much the function changes from 0 to 1, we'll do the antiderivative from 0 to 1 of the derivative, like so. I can go ahead and replace f of 0 with 5 because I know what that is. And now we have to look at the problem and decide how are we going to get the value of that definite integral. And if we have a graph, and this is a nice clean graph, we can find that area with geometry. That is a triangle with a base 1 and a height 6. So my final answer is going to be 5 plus the area of that triangle, half of 1 times 6, which ends up giving you 8 for f of 1. So the initial condition plus however much the function changes, which is the area under the rate of change, under the derivative. Moving on to 4. This one's worded, again, just a little bit differently. I'm trying to show you a few different ways this can be presented. So we have f is an antiderivative of that thing. I did give you right here, I do see some initial condition right here, but this problem, I see for initial condition, this problem doesn't explicitly tell you f prime equals something. It makes it a little bit more difficult. Instead, they worded it in this weird phrase, f is an antiderivative of that. So when you see that phrase, and I have it kind of simplified down here, if you ever see f is an antiderivative of g or something like that, you can interpret that 2 ways. The literal interpretation of that, verbatim, is f of x is an antiderivative of g of x. So that is a literal interpretation of that statement. However, if you differentiated both sides of that equation, you would get the derivative of the left side would be f prime is, and the derivative of the antiderivative puts you in a loop and spits you right back out to g of x. And this interpretation right here is usually the one that is going to be more beneficial as you process problems like this. So when I see f is an antiderivative of g, I will go straight to the fact that f prime is g, and I can do the same thing here. When it says capital F is the antiderivative of this, I can take this statement right here and conclude that the derivative of capital F is the natural log of x cubed over x. And with that, now I have all of the pieces I need. I have the initial condition, I have the rate of change, f prime, and I want to know what f is doing when x equals 9. And so f of 9 is going to be my initial condition, f of 1. And then to find out how much f changes from 1 to 9, we will do the antiderivative of f prime of x, which I'm going to go ahead and put the actual function in. That's the natural log of x cubed over x, and we'll measure that from 1 to 9. And again, we'll go to our handy-dandy Desmos calculator to figure out what that is. I'll see f of 1 is 0 this time, so the initial condition was kind of nice, so that's just 0. And we need to know the value of that antiderivative, so 1 to 9, close this out. I said close you out, there we go. The antiderivative, int, 1 to 9, of my function, it's a fraction, and the numerator, I believe, was the natural log of x, and the whole thing was cubed. Make sure you don't cube only the x. That was over an x times dx, and I'm going to double check and make sure I plugged that in correctly. ln of x cubed over x, and I did, and I'm getting 5.8269. And do remember, in the world of AP Calculus, you must be accurate to that third decimal, 5.8269. And in this case, on the AP exam, they would accept 826 or 827. And there's one more example that I want to look at, and this is a piggyback onto what we did at the very beginning. Same situation, people are entering an amusement park. We have the rate that people are entering. This time, though, I'm changing the question just a little bit. I'm giving you an initial amount. At time t equals 12, at time t equals 12, there are already 4,000 people in the park. And so what I might do on this one, I have a function for the rate that people are in the park. I may do this. I'm going to say A of t is the number of people who enter the park. Ooh, this is, man. Okay, I'm just seeing a slight error in how I worded this. I should have said, instead of in the park, I should have said 4,000 people have entered the park. We'll just work under the assumption nobody's leaving. The park's locked. They can't escape. They're locked in. So people are entering the park. The spirit of this question is that if I want to know, I know that at time 12 there are 4,000 people in the park. I'm curious how many people are in the park at time 17. And I have the rate of change. The rate that people are entering the park is E. So my number of people at time 17 is going to be what I start with at 4,000. And I need to see how many more entered the park from 12 to 17. And we can actually just go back to our work for number 1 a long time ago and import that answer. It was 3,000 something. I remember that. So go back here, and it was 3,494 people had entered the park. So I'm going to import that answer, 3,494, which ends up being 7,494 people in the park. And again, slight mistake in how I worded this one. I should have been more clear about people entering the park because people could be leaving theoretically. But there is the spirit of that question, and I am done with net change theorem.